All right, so we're going to warm up with a question. It's a system of equations, and setting it up is actually the problem here. So I made this one up, obviously. Santa's best elves buddy. Yes, buddy. Was busy making toy cars and dolls last night. Elves are actually paid to make toys. He's paid $1.50 for each car and $4.50 for each doll, and he made a total of $75 that night, and he produced 3 times as many dolls as cars. So we're going to ask that you, like always with systems, define your variables very clearly. And then you're going to set up your system, you're going to find a solution, and then you're going to write a sentence for your solution. So we have to start with, what are the unknown things? What are the things that we're trying to solve for? The number of cars that he made and the number of dolls that he made. So in this case, I'm letting you choose the variables, but I will warn you on the test, it doesn't let you choose. You have to use X and Y. So that's up to you. But would you like to choose a variable to represent the number of cars? X. Oh, right. X is the number of cars. So let me guess, you're going to go with Y for the number of dolls? All right. And make sure that's super specific. Don't just say like X equals cars. It has to be number of cars. So the first question, or the first statement that you're going to write is all about the money clues. And oh, dollars. Yeah, dolls. Dolls. I don't know about you. Santa gives me dollars. All right, dolls. There you go. Man, wouldn't that be nice? Just your whole stocking. Just money. All right, so number of dolls. There we go. $1.50 for each car, $4.50 for each doll, and a total of $75. That's an easy sentence for us to create. That's just 150x plus 450y equals 75. Now, this next clue, this is the one I'm worried about. And the reason I'm worried about it is because it's not written in the normal notation. It says he produced 3 times as many dolls as cars. Now, normally when you guys are translating words to algebra, it says something like the number of dolls is, or the number of cars is, and this one is not written that way. And that's what actually makes it tricky, because a lot of kids just say like 3 times things, so like your little algebra robots. But if it's not in that notation, you either have to write it in that notation or at least think it in that notation. So I suggest that you translate this part that I boxed in red here into that notation that you like. So instead of saying he produced 3 times as many dolls as cars, we could reword this as the number of dolls is 3 times the number of cars. So in order for you to just straight translate to algebra, it has to be written in that sort of notation. So the number of dolls, which we know is y, is 3 times the number of cars. Now, another way to get that red statement is to think about it like a balanced scale. If it says 3 times as many dolls as cars, that means you would have to multiply the number of cars by 3 to get it to equal the same number as you have dolls. That's the backwards thing of algebra working, right? So that's kind of tricky to set up because it's not written in the traditional sense. So now they're going to ask you to solve it, and I think this is a great candidate for substitution. I would substitute in 3x in place of this y, and then I would solve. So 1.5x plus 4.5, we're not going to do y anymore, we're going to call it 3x, equals 75, and when you add this together you get 15x equals 75, so x equals 5. And then go back and plug it in for y, and you get y equals 15. Now, before I commit to this answer, stop and think about what you just wrote down. X is the number of cars, and 15 is the number of dolls. And remember that weird clue that was kind of giving us pause? It says 3 times as many dolls as cars. Did you end up with 3 times as many dolls as cars? We did, so we could feel like we've done this right. You just have to be really wary when you get to a question worded funny that you kind of have to stop and come back and say like, oh, I hope I didn't mess that up. Because these are very easy to mess up. All right, so they're going to want you to write a sentence. I'm not going to write it because I'm out of space, but you would, let's verbalize it. It would say, you know, he made 5 cars and 15 dolls last night. That would be a great sentence. All right, As far as warming up, that was it for us today. Let's get lesson 6.2, which is worksheet 10 out. Now, with us being so short on time, we're going to give a very quick version of this lesson. We're going to skip a major part of it. I'm going to try to explain it as best I can without showing you the full lesson. And then it's going to be one of those magic moments on your calculator again today, which I think you're all okay with that at this point. You need a little bit of a win. All right, so the first concept in this lesson that I want to talk about is how matrices can be used in like real life problems and how they can organize data. So the question that they're throwing up at you here is about competitive skating. And we have 3 skaters, Holly, Joelle, and Louisa. And they are being judged on different criteria for different skating score systems. And this does happen. Like I remember a decade ago or so, they changed the way they used to score gymnastics in the Olympics and everyone was freaking out, right? So depending on which system they're being scored on, each of these figure skaters are going to have a favorable system versus a non-favorable system. So like system A counts choreography as 50%, which is the most in that system. But in system B, skating skill is counted as the highest. So I guess it depends on how this child is doing or this person is doing as a figure skater. Here's their scores on their last competition. So our job is to figure out which skater prefers which method. So this data, all the skaters and their criteria judging scores, is a 3x3 matrix. And this matrix over here, this data, is talking to you about the percentages that each criteria gets in each of the systems. So we're going to enter this guy into matrix A as a 3x3. And we're going to enter this guy into matrix B as a 3x2. But I'm going to need you to put this as 0.2, 0.5, 0.3. So the decimal versions of all these percents, please. I'm going to pause the video, viewers pause and start entering as well. So matrix A was the results from the skaters' scores, and then matrix B is where I entered all the system percentages. So what we're going to do now is multiply matrix A times matrix B. So we're going to pull up matrix A times matrix B. Boop. And then it's going to produce that. So what we have to go back and think about is what is our result and how can I interpret that? So your first matrix, matrix A, when you're multiplying them, remember this is where we took the row of this matrix, all the rows, and we took the columns of the second matrix. So when you get a result of 3.8 in this first position and 4.2 in the second position, what that's telling you is the first row is Holly, the second row is Joelle, and the third row is Louisa. And then the first column is system A, and the second column is system B. Thank you. So for Holly, she's going to be scoring a higher average, a score, on system B. So when you look at Joelle, she was a 3.4 versus a 3, I believe. So it looks like Joelle is benefiting from system A. And then Louisa was 4.2 and 3.8. So Louisa is also benefiting more from system A. So that's a neat example of how you can take lots of information, apply multiple problems to the same thing, which is matrix operations, and then create all of your solutions all in one sitting. It's just your job is to interpret the matrix, which can be tough. So you just got to really be careful about what rows and what columns you're taking. There's a question coming up on your test that talks about like inventory at a store and then like how much everything costs, and you got to make sure you've got the right thing in the rows and the right thing in the columns. So, all right, so this is the part where I get to give you a horrible, horrible, horrible explanation of what magic your calculator is about to do. So let me think of a good place to start. All right, you don't have to write any of this down. This is just kind of for your knowledge. When you are trying to solve, so like we have matrix A, let's say, and you're multiplying it by matrix B, and it equals matrix C. What if I said your job is to figure out how to solve for matrix B? What if that's the thing that I don't know or the thing I'm trying to find? So a really good gut instinct answer from anybody at this point who's new to matrices would be, oh, Mrs. Brousseau, just divide matrix A over here. And I understand why kids tell me that because it makes logical sense when you think of linear algebra, but these are matrices, which are like functions on top of functions. So you actually can't divide by a matrix. What you're going to have to do is apply the inverse matrix in order to move it. And I use the word move very liberally. You're not really moving anything. So if you apply the inverse matrix of A to matrix A, basically an inverse and an original matrix undo each other, and they end up giving you the identity matrix that we kind of saw yesterday that looked like this. I'm just using a 2x2 so I have less writing. The identity matrix is the equivalent of the number 1 in like normal number systems. So if you just have a 1 sitting in front of your solution, it doesn't really do anything to your solution. So you've solved for your solution essentially. It's the same idea as when you guys had 3x equals 12. I know you guys think of dividing by 3, but what you're really doing is the mathematical inverse of multiplying by 3. The mathematical inverse of multiplying by 3 is to multiply by 1 over 3. You just don't think of it that way because that's not the way you were taught, you know? So, guys, talk to me for a minute, though. What is 1/3 times 3? It's 1. Yeah, so there's still a number there. It's just the number 1, so you guys just don't ever write it down. So same idea here. You end up with what is equivalent to the number 1 in matrix land. So the number 1 times matrix B is essentially just saying matrix B. Now think about it this way. You have good gut instincts here, guys. If you did something to the left side of an equation, doesn't your instinct tell you you probably have to do it to the right side as well? So not only do you have to apply the inverse over here on the left side, you're also applying the inverse of matrix A over here on the right side. So turns out, if I want to solve for matrix B, what I would have to figure out, hopefully on my calculator, is whatever matrix A inverse is times this original matrix C from the solution side. Whatever that is, that's my solution to B. So that was super fun. What I need you to do now is skip over a whole bunch of these notes. They go into great detail about how you find inverses of matrices. I am not going to have you guys find inverses of matrices unless you want to use your calculator, which is what we're going to be doing today. So forget how you find inverses. Just know that you can find them by hand. And I want you to all feel bad for me because I did have to find them by hand and compute everything we're about to do. I had to do by hand. Back in my day, it was one of those, you know. So we don't have time. So skip it. I'm sure there's a great Khan Academy video that'll explain all about it. That man knows everything. How does he know everything? Anyone ever watch that? He's smart. Like super smart. Man. Alright. Skip all the way to the back, please. I need you to find this question. So it's almost in the middle of the back page, which tells you how quick we're going to go through this lesson. So here's what we're going to do. I'm going to give you a matrix system, and I'm going to have you write it as a matrix equation. So a little different from yesterday. Yesterday, you guys would just enter this as a 2x3 and then perform the magic that is RREF to it, and then it would give you the solution in an augmented matrix form. It was great, and you're still allowed to do that. But another thing I need you to understand is all about notation. So you're going to have to take this system and be able to break it up into, now write this part down, the first matrix, these are going to be your coefficients. And then the second matrix is going to be your variables. And then those are multiplied together. And then it says equals, and then your last matrix over here are going to be your solutions. Now all of those vocab terms I'm referring to are from the system. So you take the coefficients from the system, just the body coefficients. You multiply it by the unknown things, which are the variables. So in this example's case, x and y. And then you set up your final matrix as the solutions to your equations. So that's what they've already done for you guys here. Now let's stop and think about why this setup works. Matrix A, remember, are the coefficients, and we know when we multiply matrices together, you're supposed to take the rows of the first matrix and the column of the second matrix. So this is that thing we did the other day with like left pointer finger on the row and right pointer finger on the column when we started moving. So think about this, guys. This first row multiplied by this first column would be 3x minus 7y. And look what your system was, 3x minus 7y. So it's just taking what we already know is the multiplication problem and pulling it apart. And then equals negative 16 is obvious because it equals negative 16. So same thing here. This is negative 1x plus 2y equals 8. So taking a system of equations, breaking it into a matrix equation. It's gross, I know. All right, so this is what's going to happen. I'm going to show you what like you would have had to know how to do by hand maybe back in the day, my day. And maybe when you go to college, because there are still professors out there who require you to do these by hand. It's awful, and I apologize if that happens to you. I just want to show you what's going on, guys. So the whole point of this question is to solve for x and y. So think about this. I'm trying to solve for x and y, and it's sitting in this matrix. So rewind your brain for a minute. This matrix can't be here anymore. How do I, quote, get rid of the coefficient matrix? I multiply by the inverse of this matrix. So just for shorthand notation, because I'm sick of writing the word coefficient, I'm going to call this matrix C. So if I apply the inverse of matrix C over here on the left side of my equation, I also have to multiply the inverse of matrix C over here on the right side of the equation. So for you guys are going to think of these as just canceling each other out, and that's okay. But what's really happening is it ends up giving you what's called the identity matrix, which looks like this, which we know is secretly just like the number 1. And then remember, we haven't done anything with this variable matrix yet, which is xy. I just changed colors for no reason. Sorry about that. Now this is the magic part. Since you guys don't know how to find matrices by hand, if you don't know how to find inverses by hand, there's no way for you to do this part by hand. So you're going to have to type exactly what you see on your calculator. So this is where we're going to grab our calculator. All right, guys, everybody, please enter what you see here. Enter this matrix into matrix A, and then your solutions matrix B over here. Change my colors back. Enter this as matrix B. I'm going to pause the video. Viewers pause and enter as well. Alright, so instead of writing out the full matrix, I'm just using like some colors and some variables to represent. So matrix A times this variable matrix equals B. We know that in order to solve for this red matrix here, the variable one, we're going to have to apply the inverse matrix of A times A. Don't do anything yet. And then you have to do it over here as well, the inverse matrix of A times B. Notice how I wrote matrix A inverse first. Here's what's happening, guys. When you apply inverse matrix A times matrix A, we talked about we're just getting what's called the identity function, which is the matrix equivalent of the number 1, times the matrix xy. And then this is where you are definitely going to grab your calculator, because I don't want you to learn how to do this by hand. So on your calculator, could you please type A inverse? So your next question is, Abruzzo, how do I type A inverse? Well, I don't have the matrix entered right now, but I do have a matrix entered. You're going to pull up the matrix using the names, and then you just hit the inverse key, which is this guy right here. You could raise it to the negative first power, I believe, as well, but there's a whole key made for inverses, so just use it. And then you do times matrix B. So I don't have the right matrices in, so I'm not going to be able to help you there. But you're going to help me by giving me the resultant solution, please. Negative 24, negative 8. Are they both negative? Did I hear you right? Okay. So here's where we have to, like, yay, we used our technology, but now we have to interpret the solution. The identity matrix is just saying 1x equals negative 24. All right. And then the identity matrix here says 1y equals negative 8. So that was another way for you to find your solution. But you guys are like, wait. We just did this yesterday, and it seemed a whole lot easier. So let's think about yesterday for a minute, guys. Yesterday, when I gave you that system, the original 2-variable system up here, how would you have entered this as one singular matrix? What would have been the dimensions on this original matrix? A 2 by 3. So you would have entered the whole shebang as a 2 by 3. And then you would have done, remember the command on the math menu? RREF of, whoops, it's supposed to be a matrix, of whatever that matrix was. And then your answer came out to that augmented, it would have said like 1, 0, negative 24, and 0, 1, negative 8. So here's where I understand. If I'm on a test and my teacher says, solve it, even if the directions say solve it with a matrix equation, I'm going to humor my teacher by writing this down, and then I'm going to solve it however I want, which is going to be an augmented matrix with RREF, because it's less typing, right? You don't have to worry about inverse matrix applications and things. So on your test, I'm going to require that you understand how to break it into the proper notation, but I frankly don't care how you solve it. Okay? All right. Let's get this one entered, but you know what? I lied. Let's not do that one. Now, I chose poorly on the last class. I made them do number 10, and after we got everything written out, turns out that this matrix has no solution. So that's a bummer. Let's hope for the best on number 8. I don't know if 8 has a solution, so here's what I'm going to ask you on a test. I'm going to ask if you could please break this into a matrix multiplication statement. So remember, that's like matrix A times your variable matrix equals your solutions matrix. Now on your test, man, we really babied you guys. I gave you like a full-out skeleton. All you need to do for me is like put things in their place. So remember what goes in this first matrix? All of your coefficients from the body of your system. But be careful, everything's in a little bit of order. You got order problems here on the second equation. Your coefficients are 1, negative 1, and 2. Can someone help me with the lead coefficients on the second equation though? I heard 1, 0, negative 1. Thank you. And then 3, 2, 1. This is the variable matrix. So which variables did they use in order, please? X first, and then Y, and then Z. Very nice. And then this is the solutions matrix. Solutions in order are 5, negative 4, and 0. So this is where you get to kind of do what you want. I need you to solve this system. You can either use the augmented matrix from yesterday using RREF, or you could do this A inverse times B business if you really feel you need to. Your teacher won't know any better. That's me. I don't care. And guys, I don't even do the inverse stuff. I always use RREF because it's easier for me. Since I'm too lazy to type, I'm hoping one of you wonderful children can tell me what your calculator spit out at you. Negative 1, 0, and 3? Okay. So can you please interpret that solution for me? As an ordered triple, you would write literally what she just said. So negative 1 was your X, 0 was your Y, and 3 was your Z. Nice job. So that's, as far as like what are you going to have to do on a test, that's it. Can you break it up into a matrix multiplication equation, and then can you use your favorite method to solve it? So as far as the lesson goes, guys, I'd like to stop the lesson there, because I have something very important to talk to you about. Cookies and cookies and cookies. Can you find worksheet 12? And then find the back of worksheet 12. Oh, by the way, you have 2 pages, but it's like just a couple problems on each page. That's your bookwork assignment that's added for tonight. That's on this matrix multiplication fun. And remember, I gave you guys printouts of the bookwork. If I missed you on that, I have extra copies over on the table. But I need you guys to find this problem on worksheet 12, side B. $12 is part of your homework check. I'm going to do the harder problem with you, which is side B, and then you're going to do the easy one for homework, which is side A. Got it? All right, so I love this question because I like cookies. I like baking cookies. I like eating cookies. This is all about cookies. We got Jack and Jill. They own a small bakery, and they're making fresh cookies daily. They bake 2 kinds of cookies, plain and cookies with icing. I feel like Jack and Jill are going to go out of business. This doesn't seem well thought out. Anywho, the cookies are sold by the box. Jack and Jill are confident that they can sell every cookie that they make. And there are natural constraints to the problem, and there are other constraints to the problem. For instance, you can't make -5 boxes of cookies, right? So you can make 0 boxes of cookies. You can make integer value of cookies after that. So 1 box, 2 box, 3 box, and so on. But there's other logistical problems that they have to think about because they own a business. So the dough, for instance, they only have 72 pounds of cookie dough in their kitchen. And they know from their experience that plain cookies require 1.2 pounds of cookie dough for a box. And then iced cookies require 0.9 pounds of cookie dough for a box. So there's also similar constraints for the icing. In their store, they have 20 pounds of icing. But then plain cookies don't take any icing, but the other cookies take 0.4 pounds of icing per box. And then just, frankly, time is a constraint. There's only so many hours in the day. So it takes 0.10 hour to prepare a box of plain cookies. It takes 0.15 hour to prepare a box of decorated cookies. And Jack and Jill together, they only have 9 hours today to work. So they took the fun out of it for you. They went ahead and said, let X represent the number of boxes of plain cookies and let Y represent the number of boxes of iced cookies. All right, what we're going to do now is we're going to come up with what are called constraints. And I always like to start with the natural constraints. Like, for instance, the number of plain boxes of cookies has to be greater than or equal to 0. Can't have negative boxes of cookies. And then same thing with the decorated cookies. They have to be greater than or equal to 0. All that does when we go to the graphing step is it restricts you to the first quadrant, which you guys probably would have restricted yourself naturally because they only show you the first quadrant down there. But if you guys were solving these from a textbook question, they wouldn't give you any sort of a graph and you'd have to figure it out. Alright, so now let's talk about the cookie dough. 1 plain box of cookies requires 1.2 pounds of cookie dough. So 1.2 for a plain box, and then 0.9 for the other kind of cookie, the decorated kind. And they only have 72 pounds of cookie dough. So that means you cannot use more than 72 pounds of cookie dough. So the inequality I'm looking for here, guys, is less than or equal to 72. You're going to run out of cookie dough if you go beyond that. And then we have some clues about the icing. Plain cookies don't have any icing, so nothing there. But 0.4 pounds of icing are used on the other kind of cookie, and you can't exceed 20 pounds of icing, because that's all you have. Get some room here. And then time is its own constraint. So it requires 0.1 hours for the plain cookie, and then 0.15 hours for the decorated cookie. And all the time added together cannot exceed 9 hours, so less than or equal to 9. So what you're going to have to do now is you're going to have to graph what is a system of linear inequalities. The first two that I wrote in black are boring and obvious. They just restrict you to the first quadrant. But the one that's blue, green, and red, they're all in what is essentially standard form and not really a great form for me graphing. So what I would like you guys to do is help me manipulate this equation so that y is isolated. So in other words, you need to subtract the 1.2x over, and then you got to divide everything by a 0.9. So y is less than or equal to, the first term is negative 1.2 divided by 0.9. Can I get some calculator help on that? What is negative 1.2 divided by 0.9? Math enter, because it is a fraction. Negative 4/3. Okay. So negative 4/3 x plus, and what happened when you took 72 and divided it by 0.9? 80, thank you. So that's the new blue equation. That's one I can graph. Now for this green one, that one you just got to divide both sides by 0.4. So in slope-intercept form, it is now y is less, well, in a better graphing form, y is less than or equal to 50. Okay. And then for the red one, it's just like the blue one. You got to subtract the 0.1x over and then divide everything by 0.15. So y is less than or equal to, what is negative 0.1 divided by 0.15? Math enter, please. Negative 2/3, thank you. And then 9 divided by 0.15? Is that 60? Okay. So these are the ones we're going to have to graph. Here we go. All right, so that first blue one, it was -4/3 plus 80, I believe. So it starts up here at 80. And even though the axes are counting by tens, you can always count slope just by boxes regardless of the units because they're equally spaced. So like for instance, going down 4/3 is the same thing as going down 40 and over 30. So I'm just going to count boxes because I can't really do anything else. I'm going to move down 1, 2, 3, 4, right 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. And I'm going to hope for the best because now I got to graph a line. Oh, so close. All right, so then I have that green function, which was y. I won't shade yet. I'll say for the end. Y is less than or equal to 50. So that would be just a horizontal line here at 50. And then that last red one, I believe it started at 60. Was this a -2/3 on that one? Okay. So down 1, 2, right 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. And yep, totally okay. I hit some of those points. That was good. So remember, all of these inequalities that we were trying to graph, they all said less than, less than, less than. So if you think about graphing underneath the red line, underneath the green line, and underneath the blue line, what you're ending up shading is this weird polygon that is not quite a, well, I guess it is kind of a trapezoid, isn't it? It's weird. I don't even know. I mean, I drew it, so who knows what it's supposed to look like. But it really doesn't matter, guys, because here's what's important to this picture. The intersection of all of the boundaries. So in other words, the vertices to this polygon. So that's a vertex, that's a vertex, this is a vertex, and this is a vertex. So we're going to have a full-out lesson on this tomorrow, but this is just kind of leading it into it. All of these vertices are what we refer to as critical points on this optimization problem, is what it's going to be called tomorrow. So the really boring vertex at 0, 0, and then this guy is at 60, 0. Up here you're at 30, 40. And then over here you're at 0, 50. So here's what I know because of math. Math says that if you create a bounded region like this, and you can now create a profit function, they're going to know how much money they make off of every item they sell. Your maximum profit will occur at one of your critical points. So let's talk about profit function. Keep reading on the page. It starts talking to you about money. And it says the profit on a plain box of cookies is $2 and the profit on a box of iced cookies is $3. So we're going to determine what's called a profit function. We'll call it P of XY. And it's $2 for every plain box and $3 for every iced box. So here's what you have to do. You got to take all those critical points we just found and plug them into that profit function that we just wrote down. And it wasn't real difficult, right? It was 2x plus 3y. All right, here we go. If you plug in 0, 0, you get nothing. Well, that makes sense. You're not making any cookies, y'all. You're not going to make money. If you plug in 60, 0, you get 120. If you plug in 30 here and 40 here, you get 60 plus 120. Is that 180? Cool. If you plug in 0, 50, you get 150. So all the stuff in the boundary is going to be less than the greatest one we just found. And who was the greatest one? 30, 40 gave you a max profit of $180. So that's what we have to report back to Jack and Jill. That they should make $30 boxes of plain cookies and 40 boxes of iced cookies for a max profit of $180. Ta-da! Now that was a pretty babyish example, if you will, because, you know, obviously Jack and Jill are not going to go hire a data analyst to tell them this answer. They're probably just going to kind of live and learn. Oh, we made too many cookies today, and they'll take a loss for a while. But like big name companies, they go through analytics like this quite a bit. It's way more complicated than what we just did. But the idea is, I'm a business. I want to make the most amount of profit as I can. Tell me how I can do that. And the person that they hire to tell them how to do that gets paid a ton of money. So that is under the umbrella of analytics. And those of you who are wonderful at math, guess what? All of you. If that sounds any sort of interesting to you, maybe explore that in your college, because that is a huge field right now. You're not going to be doing cookies and cupcakes and whatever questions. You're going to be doing something more exciting, but big field in college, in industry right now. All right, that's the lesson. So your homework, you're going to finish worksheet 12, and then you have those couple of book problems there. Since you guys have about 5 minutes in class, I suggest you just flip worksheet 12 over and try to finish it real fast. A side note on the video, there was a whole other critical point I missed. And if we go back, this point right here also would be considered critical. And if you actually found the intersection of the green and the red, which y equals 50, I'd have to go back to the equation here. Plugging in a 50 into the red function, either version of it, would be negative 2/3. Nope, ignore me. That's the wrong thing to do. Where are we at? So this function equals that function. So what you'd have to set up is 50 equals the red function, which was negative 2/3 plus 60. Oops, x plus 60. I already know the y is 50. And if I solved for that, I would subtract 60 and get negative 10. And then I'd multiply by the reciprocal, 3/2. And I would get, what do I get? Negative, no, I did something stupid here. That's positive 10. All right, so anyways, I would get 15. There we go. 15 is x. So that intersection point is 15 comma 50. And when I go plug that into my profit function, I get 2 times 15, so 30 plus 3 times, okay. So we end up with 180 anyways. So back up. My answer technically has two possibilities. They could either make 30 boxes of plain cookies and 40 boxes of iced cookies, or they could make, 15 boxes of plain and 50 boxes of iced. So I guess it's up to Jack and Jill to decide what works. Sorry. Good call, Garrett.